Hello, everybody. This is going to be our video lecture on isolated and its cousins in the Java space of synchronized. We'll touch on deadlock, a bunch of things. So let's just get into it. So first of all, this is the quiz for today. This is an example from the Rice videos. And what I want you to do is, here's a program that has three asyncs, A, B, and C, each of which touch this accessible mutable data X. And two of them, A and B, are globally isolated, but block C isn't. So the first question for everybody is, what can run in parallel with A, what can run in parallel with B, and what can run in parallel with C? So like, can B and C run in parallel with A? What can run with each other? And so the next question is going to be from their quiz, which is how many different ways can you serialize the reads and writes to these? The question after that is finding the data races here in MutaPoint. So pause and go through this and get your answers, and we will come back. All right, so we're back. So let's talk about this real quick. What can run in parallel with each other? As I pointed out, A and B are isolated, so they're acquired global lock, if you will, in X10. And so anyone else who's done this also will not go in. So A and B cannot run in parallel with each other, but A can run in parallel. Let me go back here, sorry. A can, in fact, run in parallel with C. B can run in parallel with C, and of course, C can run in parallel with A and B, okay? A can B, we'll just leave them in there. And so the next question is much harder. How do we calculate the number of different ways to serialize the reads and writes? This is a Q&S question. Like, can you please explain this to me? A number of people ask that. Another quick question is, and this question is, why is the read and write within async, why is it that they don't operate sequentially? They do, just not atomically. And we'll talk about that more today and the next time. The key is that they can be split in half. So you can like be halfway through it and someone else gets a chance to go. I mean, the whole point is that things can run in parallel with each other. And so if you're accessing mutable data, you can get into trouble. So the answer to this question is 5 plus 4 plus 3 plus 2 plus 1 times 2, so 30. But let's go through the answer. Let's go how we acquire this answer. So let's talk about this real quick. They give a little hint on like, don't waste a lot of time, think of how to solve this problem. So let's go through this a little bit. The high-level plan that I'm going to use is I'm going to use A and B as my anchors and count all the ways that C can interleave with them. I mean, their reads and writes, what they can fit in between, what they can wrap around. So since A then B and B then A will have the same count, then I can just figure out for one of them and then multiply by 2. So that's going to be the plan. So what I want you to imagine is so we're going to go with this A happens first and then B happens. And like I said, the exact same thing, the exact same scenarios that I play out will also happen for B first and then A. So that's why we're going to multiply by 2. So in this situation, I want you to imagine the read of C's X right here when I'm going to read X, right, before I add and then write to X. That happens before anything, before A is read or written. There's 5 basic spots that the write can happen. It can happen before A has done anything. It can happen in the middle of A. It can happen between A and B. It can happen in the middle of B or in the end of B. So those are the 5 cases that can happen if C reads before A even goes. If C reads in the middle of A, between A's read and write, then there are 4 spots. It can write before, right between the 2, right here, right here. So there's 4 of those. You might imagine there's 3 of these. If you read between A and B, then the write can happen between, or it can happen, or between A and B, or it can happen between B's read and write, or after the whole thing. You might imagine there's 1 in here, and there's 2 spots. And if C reads after these 2 have gone, then there's really only 1 place for its write to happen, which is also afterwards. Okay. Another question is, couldn't like we avoid the data writes by being clever and reading right into some variables or adding temps or something? I mean, at the end of the day, if you read and write and can get interrupted. Like a plus plus can get interrupted, or excuse me, not interrupted, can be split apart and have a data race. Then how is adding more variables and more writing to things going to make the window smaller? It's just going to make the window bigger. And there is some crazy thing that you can do, which anybody who's interested in, there's some things you can do, but that's the subject of a Professor Lee course, let's just say. Okay, so another question that came up that a lot of people ask for is like, so assume that A and B are isolated. Yeah, how many different values can it end up with? This answer is 5, which is also not necessarily the most clear thing. Let's talk about the 5 and why they can happen. Okay, they are like, C is the only one that happens. A and B happen, A and C happen, B and C happen, or all 3 happen. And you end up with these 5 different values. And let's talk about it. It has a nice explanation, and I'm going to break it down a little bit here. So first of all, addition is commutative, which some people might be like, hey, isn't that subtraction there? Hopefully, grab me an office hours if this is confusing, but this is more like adding 3 numbers, one of which is negative. And if that is confusing, hop on to office hours and we'll talk about it. And so we'll go back to that later. But like I said, this is much more like an addition of a negative number, which is commutative. But I can see why that was confusing to a couple people. So there's 8 total cases. Let's eliminate 3 of them. The nothing happens case. Well, at least one of these reads and writes is going to happen, right? Like somebody's writing their value out to X, right? So it's not that none of them can happen. So that one's eliminated. There's another case that can happen, which would be that only A happened. Only A's work was contributed, right? But that can't happen because A can't envelop B, right? And so like with that, then the case where only A happens is out. And the case where only B happens is out is the same reason, except, like B cannot envelop A. So let's talk about the 5 other ones. Here's one of them. Here's one of the 5. It's that C is the only person whose work ends up being affected. You read from C. A does its reads X, writes X. B reads X, writes X. Like they've got this nice value sitting over in X, right? So A reads 0. C reads 0. A writes out 2. B's like, awesome. I'll read 2, subtract 3 from it, write -1. And C is like, yeah, I don't care what either one of you did. I read 0, I'm adding 1, and I'm done. Okay, and so that's how we get only C's value. A, B happen would be like, this is one of the cases where C reads in the middle of A. A is in this way clobbering C. B could do the same thing down here. If B and C's work are the only ones that end up getting contributing to the final value of X, that could be easily done by like C reading here, writing here. A's work is lost in that case. A and C is the same thing. C somehow envelops B. And A, B, and C, there's, it could go here, it could go here, or it could go here. But this is where they all get to contribute to the final value of X. Another quick way to look at it is you can just think about like what values are lost. I was kind of going through that right there. But I'll leave these slides in for anybody who's interested, and talk to me if you're still a little confused about that. The second part of today's quiz was, all right, I want you to imagine this very simple program. It's got a mutable int. Here's the definition of that mutable int. Here's a program that we're going to play blackjack, I guess, and try to add 11 and 10 to this and print it out when we're done. If you didn't finish this before, do it now. I want you to encircle all the lines that contribute to a data race. Okay, and we're back. And so I'd say there's a couple of different ways you can do this. One way that people normally fill this out is they just circle these 2 adds, which is a fine way to go. Another way you can approach it is to sort of encircle like, well, here's where the data race is. It's actually in mutable int. It's this plus equals. If you were going to do that, you should also probably do the read out as well. That's where anyone could possibly be reading the value in a data race. That's for this guy. Obviously, no one who is doing a data race over here is reading it, but the reads are technically part of the data race. So if we're going to encircle them over here, this could contribute to a potential data race. Now, that's it for the quiz. Obviously, we're not turning in the quizzes this semester, but let's just move on. Okay, so some quick questions. Is it just me, or do isolated and futures kind of do the same thing? No, is the answer. That's why we're going to cover this. Future spawns a task which returns a value, and isolated is all about protecting a critical section of code. So one of them creates a task that returns a value and is all about running things in parallel. Isolated is more like, okay, we got multiple things working in parallel, and I want to make it so that I've got a critical section of code that would be a data race if I let people, multiple tasks access it. If two come in at the same time and try to get at this critical section, I'll line them up and turn them into one at a time, sort of sequentially. And so sort of moving on to that, it seems like that as we ensure determinism, we eliminate some parallelism. Yes, we do. Or more like isolated makes non-deterministic code, takes out data races. So just because they're non-deterministic, but sometimes that's correct. So for example, in the Quicksort lab, you ended up adding tasks to a concurrent link queue. They're not necessarily in some specific order. We said we were going to do things in parallel, so we're giving up the ability to control what order they're in. As long as it doesn't lose any of them, as long as it keeps track of them all, then it's still correct, if you will. And so for this version, we're going to add A, B, and C. If it's a thread-safe data structure, right, you won't know what order they're in, but at least you'll have A, B, and C in it. If it's not thread-safe, it might crash, you might lose some of them, anything could happen. And so oftentimes, even though it's not deterministic what order it's in, sometimes it's correct, which is a very important thing. Question about what is deadlock? Let's talk about this really quickly. We will cover it more soon. I'm confused about deadlock freeze advantages. So what is deadlock? So one of the, my quick example for this is I want you to imagine two tasks, and they've come up to an intersection, and one of them is a timid task, and that task always yields, right? It just will never go. It's going to wait until everyone's gone before it goes. And then we have another task, which is the stickler for the rules, right? Like they're like, I will always obey the right of way. If you ever get a situation where the timid task has the right of way and the stickler for the rules will never go, then you're just going to be stuck forever, right? And so that is a liveness problem. That's sort of a way to think about how this is going, is that you're in a situation where no one's ever going to progress, and that's referred to as a liveness problem. So I should probably relabel this liveness right now. It's a liveness problem, and you're in big trouble. Speaking of traffic, I would play this video, but I'm not sure that the video capture would do very well of it. I encourage you to do this. Apparently, France has rotaries. Rotaries are nice. They're actually more efficient, have fewer accidents and a bunch of things. They have this crazy tradition, which I guess they've fixed in most of France, priority on the right. This seems like a traffic law that's designed to make deadlock. So everyone, you always, the rule is that the person that's coming in from the right has the priority, which if you have a completely full rotary would by definition lock. So yeah, that's not a good idea, so let's not do that. Another question that comes up is that people have asked about, like, what's a semaphore? People ask it. Those of you who've taken operating system class probably have mentioned a semaphore. In the operating system class I took forever ago, they had us build a semaphore and then immediately showed how they can produce deadlock. Like that's their superpower. Deadlocking is not a good thing, but let's sort of show off where, well, first of all, semaphores come from, these are semaphores in the train world, and they're used to protect critical sections of train tracks. So I want you to imagine these two train tracks come together in a narrow section where you're only going to have one track for a while. They came up with these semaphores to make it so that two trains wouldn't use that same set of track. at the same time to prevent crashes. This is very important. This is a very good analogy to what semaphores and locks and a bunch of things do in computer science. We try to make it so there's a critical section where only one task is allowed to use it. Make it so that only one of them uses it at the same time. A classic example of this is the dining philosophers. Can you give an example of deadlock? In this scenario, you imagine 5 philosophers are sitting around the table. Like philosophers, they do a lot of thinking. This is analogous to CPUs. And every now and then they decide they're hungry and they go to eat some rice. And that's an analogy to going to I/O. So going to disk, going to the network, whatever you want to think about it. Each one of them, they're between each philosopher, there's a chopstick. So there's 5 philosophers, 5 chopsticks. And each one of them, this is the process that is, or the task that is a philosopher. They while through, they think, and every now and then they decide to grab the right chopstick and grab the left chopstick. When they've got them both, then they'll start eating. And when they're done, they'll put down both chopsticks and then they'll go back to thinking. And so this can deadlock. I want everyone to pause the video and think about how it can go poorly. Okay, and we're back. So hopefully at least some of you came up with the idea that if all of them grab the right chopstick, right, and then all of them go to grab the left chopstick, but the philosopher to their left has the right chopstick, you can end up with a cycle. And this is deadlock, right? There's a set of resources, there's a cycle, and everyone's got one of them, everyone's waiting on the other person, and no one will ever recover, okay? And so I want you all to spend the next couple of days thinking about how you would get out of this deadlock. If I get caught up, I might even post a scenario for everyone to fill out in time for an upcoming lecture. But I want everyone to think about how they would go about recovering from this sort of situation or preventing this deadlock from happening, okay? Easiest ways to prevent and do that, we'll talk about that later, okay? How you can get into this situation in Java is monumentally easy. If one task synchronizes on A, then B, and then another task synchronizes on B, then A, then you can absolutely deadlock. And Java's tutorial basically just gives examples of just how easy it is to deadlock. Everyone seems to think this is okay. Java's official policy is you're on your own. Invoking objects, methods from synchronized code can create problems, right? Like it's just like, if you call a method, you're basically asking for trouble and you're on your own. People asked a bunch of questions like, what is the difference between isolated and synchronized? They're certainly very similar. One of them is that isolated does not produce deadlock. And so how this works is X10 or Habanero is the rice version of it, orders the locks for you. And so we'll talk about that in a little bit, right? Like I said, this right here is sadness and deadlock. When you are in Habanero, you would just say, no, 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 give me both, right? And if you ask one AB and one BA, it'll make everything work for you so that it's okay. Okay. A little bit of nesting isolation that they talk about is that Habanero allows you to grab a subset of them, but otherwise just says this could be a problem. So because it can't save you from this, in Java, every single one of these might deadlock or might be fine. In this one, if you ever did code like this, it would throw a runtime exception to just let you know that this could be a problem. And I think it's debatable about which one is better. I kind of like this one, and depending on the system that I'm building. If I'm building a pacemaker, I definitely want this when I'm building it and testing it and everything. I might switch over to like let it go and hopefully it's okay once I sew it inside somebody. But it's nice to know that, oh, by the way, as soon as possible, this could be a problem, as opposed to this, which could deadlock after I sewed the pacemaker inside someone. And again, just sort of the on your own kind of attitude is very different from Habanero or X10, which said, we will order this for you and make it so it can never deadlock. There's another difference is that isolated has a global lock. You can imagine building this in Java, but then everyone would have to use this who did object-based. Everyone would have to agree to use this. And so I've never seen another system that has this sort of global lock situation. In this course, we will actually not be using isolated. I think it's nice that we got to see it. But instead, it felt more useful to use Java's direct properties or implicit and explicit locks, and then have studios to learn how to build the wonderful properties of the isolated construct. It seemed more useful to do that. And so let's talk about the precise synchronization that they're talking about. The low contention, he's says to go ahead and use global isolation. That's because the overhead is lower for global isolation because you don't have to do that ordering I was mentioning. Medium contention, that's for the object-based isolation. And this is one of my favorite little parts of his course or his videos is like, if you have high contention, you've got to go back to the drawing board because nothing can save you from that. And so what I'll say is that most of the time you end up using object-based like isolation in Java. You use explicit locks or synchronized or something like that, or the implicit locks. So that sort of falls into this category. And like if you are trying to write parallel code and everybody's constantly acquiring locks, then your code's just going to be run slower than synchronized. So you got to go back to the drawing board. Someone asked about the computation graph. I said what it looks like. We're going to cover that a little later, but essentially the computation graph has options that could possibly happen, but then plays out in one particular way. And that's how you figure that out. So like our isolators are solutions to like concurrent queue that we talked about before. Isolated's cousins, synchronized and explicit locks will be used, and atomics, which we'll cover in the next lecture, also play in building high-performing optimistic concurrency data structures like concurrent hash map and concurrent queue. I liked a lot of these questions is like, if everything is isolated, then why async them? Outstanding question. Some more along these lines. What I'd like you to think of it more appropriate is that the silly little program at the beginning that does async and immediately globally isolates to x+1 and x-2 or whatever it is. It's kind of a contrived example. What you think about it is like you've got a ton of code which can run in parallel, and then some very small critical section I want to protect, right? I'm going to do this entire search for, for the quicksort, or excuse me, I'm going to sort this entire array, and then every now and then I'm going to add a task to some concurrent link queue, right? So a small window in which you got to protect, and that's what it's sort of for. A bunch of other things along these lines about like, why on earth are we doing this? And so like if isolated is essentially a bottleneck for synchronized, if not, why don't we just, find a way to optimize the parallels? Like Professor Agrawal welcomes you to Agrawallandia. This is exactly how you should be thinking. Just make it so that everything runs perfectly in parallel, and then you'll be happy. And so hopefully the people who were thinking along these lines will enjoy some of her parallel classes in the future where everything runs in parallel and everything is sweetness of life.